to convert the difference in voltage in the unbalanced bridge into the control signal for the motor. So it may be, in analog case, it's just the amp and directly controlling the motor driver, which in turn drives the motor. Yep, please. Any question? Okay. Okay. So, and here is an example. We discussed an example of those potentiometers which are connected together mechanically with the motor. So, in fact, the rotation of motor immediately changes the resistance of the potentiometer, and bridge come into balance. Well, but the balanced bridge is not in one way how we could exploit a bridge circuit. Another alternative is use of unbalanced bridge. The unbalanced bridge, in some extent, works as a comparison device, which provides some output that is proportional to the difference between the measured resistance Rx and the resistance at which bridge is balanced. If we try to describe how the unbalanced bridge works, we may, for the first approach, and it's quite, it will be, by the way, quite accurate, we may just ignore the voltage or the resistance of the element which measures the voltage between points 1 and 2. So for the voltmeter, for the mechanical voltmeter and rather high resistances Rx or R3, R2, and 4, it's not a case. But when we use electronic circuitry, then the function of voltmeter is performed by instrumental amplifier with extremely high input resistance, and we may quite inaccurately consider that the resistance between points 1 and 2 is neglectably low. If we neglect this resistance, we actually may easily calculate the difference between voltages 1 and 2, just as a difference between voltages of two separate voltage dividers. So we have a voltage divider 1, and we have voltage divider 2. U1 is corresponding with power voltage times R2 divided by the sum between measured resistance Rx and the resistor R2, and the similar equation we will have with a voltage U2. Taking the difference, the algebraic transformation further is quite straightforward. So we just take a difference, we look at this difference, and for the simplicity, so let's consider the situation when generally all the resistances are equal to some certain resistance R, but the resistance Rx is, we represent the value of this measured resistance Rx as this balanced resistance R and some extra additional resistance. This representation is quite typical for the sensors. When we use Wheatstone bridge, for example, with a mechanical sensor, some kind of tensor resistive devices, strain gauge, or with a thermoresistors, when we're going to measure the resistance of this sensor, usually we balance bridge at normal conditions. For instance, for the mechanical meters, when Rx, it's a resistance of the strain gauge, we balance the bridge when there is no force applied to the strain gauge. And then when we apply the force and the resistance of the strain gauge just change by some delta R in comparison with initial resistance, and this difference actually is our input signal. So the difference. So because without any effect, without any force applied, so our bridge is in balance, and when we apply force to one of the transducers, one of the resistance change a little bit by delta R, so we have the voltage here, we have some voltage on the output. So if we take this equation, replace all the R except of this, all but this R1 or Rx resisted by R, and replace resistor Rx by R plus delta R, after some transformation, we actually may represent. So immediately when we don't need any simplification on neglection now, we just make the transformation and we come to such kind of equation when this delta R comes here in quite a complicated form, but we may apply the expansion in the Taylor series and transform, bearing in mind that the change in the resistance is delta R, the difference between the measured actual resistance Rx and this resistance, what this element had at balance, so it will be quite small comparing to the resistance of the wall element. So this this number delta R divided by R is quite small. So then we can expand this term in a Taylor series and write an approximate equation. Keeping here, I keep here only square term. Generally, you may add a third term with the power of 3, with the power of 4. Actually, as we know, the expansion in the Taylor series is infinite, and it contains all the powers here. But we may easily left only first two of them, and even possibly just only one of them. So just only linear term. Anyway, so we have actually some. This is in some extent a simplification, and this is an approximative result, because when delta R starts to grow high, so this highest order term starts to play more role, and we will be actually forced to keep them in mind too. So here is actually illustration of how this square term affect the relationship between the change in resistance and the output voltage of the bridge. So I took here a bridge with when all the resistance has a value of 1 kilo ohm, and feed this bridge with a 5-volt voltage. And here is the difference of this output voltage. It is a voltage between points 1 and 2 as function of the difference of change in resistance. So if this resistance of one element grows up by, for instance, to 100 ohms, it's actually more or less 5% of the total value. Sorry, not a 5, excuse me, 20%. 20% of the total value. So if we consider only linear part, so the linear part equation is shown here as a dash line, and the actual square type relationship between output voltage and resistance is the red line. As we see, the difference is actually not so big. The difference is not so big, and even if we ignore, even in this case, even if we ignore the second term, we still may operate the bridge and use the bridge in imbalanced mode up to the delta R, that is more or less 5%, plus minus 5% of the total value of R. It's quite a case for the measurement transducers. They quite seldom change resistance dramatically. So the resistance change usually is within some 5%, and even maybe even less. So this is a very good approach to convert the resistance of the transducer into output voltage. And what it's important, if we use, for instance, just a voltage divider, we may do this as well. That the advantage of the bridge, that the output of the bridge is 0, and we have no effect on the transducer. When we apply some pressure, some outer signal to the transducer, so then we have some change in output. Generally, we may estimate this error. So what will be, so if we just replace the actual line, which is red one, with a nominal line, which is a straight one, and use only this part, describing the relationship between output voltage of the bridge and the change in the voltage, yeah, so we will get some straight line. We may estimate the linearization error, and actually the linearization error, it's the error that we will get if we this change in actual resistance delta R. What we will get by replacing the actual line, which is red one, with a nominal line. So it means that if we actually, we measure some certain voltage out of the bridge, for instance, 0.2, and if we use an actual line, so the resistance that corresponds to such a output voltage of the bridge will be this one. Because, so I got it by looking when my output measured voltage crossed my red line, and look what is actually the resistance corresponding to the red line at this point. But if we use the nominal line, so this linearized line, so we read out this value of the resistance. So this is obviously the difference. So this is the difference between the measured value of the resistance and actual value. So one more, how I get a measured value? I took my output measurement and of the voltage of the bridge and recalculated using the nominal line to the resistance. This is actually the linearization error. We may express this, you may try to do it easily, but you will see that this linearization error actually depends on the range, in what range we are working. It depends on the power supply voltage, and it depends on this resistance of all the bridge elements. This one. So here is some estimation of the relative resistance measurement error if we use the unbalanced bridge. We may make a different choice of this normalization line. I took here as an example just the linear part of the Taylor expansion series for the voltage as function of the resistance. We may take any other line. Anyway, so for this line, which is actually a tangential to the actual relationship between voltage and input and resistance on the input, we may actually, if we build this error, it's quite maybe seen as well here. So here we have quite a big differences. They are less, somewhere around zero. We actually have no any differences, and then it starts to grow. So generally, this relationship between the output of measurement resistance error and the value of resistance itself looks something like that. So when our device is designed actually to operate somewhere in this temperature range, if we go to the in this resistance range, if we go farther to the upper or lower resistance ranges, so this line already will not be so simple. Is what, but it's not one more. It's not only one. There is not only one way how to select the nominal curve. So we may use, as I said, Taylor expansion. We may draw some chorda between 2 points to provide at least the smallest difference, the average difference between the actual curve and linear curve, and so on. Using the bridge, very good and very, how to say, very convenient is so-called force-sensor connection. So a good example of this force-sensor connection in different kind of mechanical strain gauge. For example, this is a strain gauge that is used as a scale for the single cell. The cell may be immobilized here, but of course it's very difficult to measure the mass of the cell itself because of very small size. And this strain gauge works in a little bit opposite way, so it vibrates all the time, and the amplitude of the vibration as it vibrates, and the amplitude of the vibration, and more often the resonance frequency of this vibration will be different for the different mass of this cantilever. So if we had some cell immobilized at the end of this cantilever, we have some cells here, so different different species of cells will provide a different resonance frequency. So actually, if we attach cell to this cantilever, its resonance frequency changes. Resonance measurements may be very accurate, but here the gauge actually works like an indicator. Is there any cell attached to it, and is there the oscillation what this device sends corresponds to the single cell or to the different type of cells? So in some way, so this strain gauge works like quite comprehensive cell scales. But how we record the deformation of the cantilever? To measure the oscillation of the cantilever, we have to measure its deformation, how it moves. And for this, the body of the gauge has this integrated circuit. It sounds very important for integrated circuit. In fact, I mean integrated because the circuit is integrated in the design of the gauge itself. But this is an approximate equivalent scheme of this circuit when B2 and sorry, yes. So this is actually internal circuit. So when we have a four resistive elements, and those four resistive elements are strain or stress sensor integrated in the silicon device. So it's some kind of silicon sensor inside the silicon. And that's actually the idea of how this four sensor connection may be done. So in fact, we have here all the four sensors. So some of the sensors react on the stretch, some of the sensors react on the strain. It may be seen by the direction of these arrows. So two of them, let's say, yeah, of this arrow. But generally, in average, all these resistors from R1 to R4 is actually equal, but equal by size. But they are placed differently. Two of them, which are in an opposite branches, is placed in such a way that the deflection of the cantilever, let's say up, cause the stretching of this sensor. So they should be here at the bottom. Another two sensors are connected to the opposite branches, the other two opposite branches, and they actually they are related to the deformation of the sensor bending down. So they, as a stretchable element, they may be fixed somewhere on the top of the cantilever. So, and this, when we vibrate the cantilever, so this resistance is one semi-period, this resistance of this diagonal higher than resistance in this diagonal, and so on. And so such kind of examples. So we need here, and here we can see the microphotograph, that here is the two type of these resistances. So those which are placed here that way, and another part which are placed in vertical like that. Working together, they provide very excellent sensitivity of the bridge circuit. The most important here to switch them correctly. So those resistors or those elements which increase the sensitivity when the outer excitation occurs should be connected in the opposite branches. And so should do the other pair of the sensors which are oriented in parallel to the cantilever, to the object axis. And for this case, we presume for the ideal situation, for the ideal resistances, that all these resistances from R1 through to R4, they all are equal, and but they all are changing when the device deforms, when the outer force is applied. These resistances are changing. These two are growing, and those two are falling. And if we made all the calculation trying to explain how it works, yes, so here you see U1, yes, because yes, it seems that this arrow is wrong. So when So when here we have some excitation, so as I said, so these resistors both change their value by delta R, but two of them increase their resistance, but two decrease their resistance. As a result, these these fractions actually diminish each other, and we got here a single fraction. That output voltage is equal to the power voltage times delta R divided by R. So the force sensor connection peculiarity is that it is not nonlinear. So we do not need to neglect anything. So they are quite linear and very well works. So here for this gauge, so one more, please take a look. So when we bend it in one side, so the sensors which are on the top will be stretched and the bottom will be compressed. And the next year they change. The next time they change, time to time, they change the polarity and measure in opposite direction. What else is important with a four sensor bridge? With such kind of bridge which is integrated into some solid state device. For instance, note here they are really integrated. So we have a separate resistances which are integrated somewhere here in the silicon, and they works well. But where is the problem? The problem is that we couldn't just easily balance this bridge just by changing the resistance of any of these elements, because they are integrated inside. To balance such a bridge, when we have no direct access to any of the resistors which is included in the branches, we may use some kind of special circuit. Here we have actually two output from one side. Yeah? We have actually here two output which may be used to switched in to connecting in some balancing resistors that actually balance the bridge. So here is an example how could we balance a bridge even when resistors R1, R3, and R1 and R4 are not equal absolutely. Now we still may balance the bridge by changing, for instance, the potential of one of the corner of the bridge. So this is actually what this circuit. Yes, this circuit it may be easily used for the zeroing. Actually, what do? We add in parallel some resistance, some part of this long regulate resistance in parallel to resistor R2, another part in parallel to resistor R3, and by changing the ratio, the position of the slider, we actually may add more resistors to R2 or more resistor to R3, hereby changing the values and balancing the bridge. This zeroing circuit, some recommended value for this zeroing circuit, the resistor Rx should be approximately 10 times bigger than these resistors in a bridge, and resistor Ry may be quite hard. It's maybe actually, yes, it corresponds to the relatively short device, and the resistance of this device should at maximum reach yes. So sorry, one more. So about this, I said that the Rx is about 10 times the resistor of the branches, individual branch, and Ry it's about 25, the resistance of individual branch. And yes, indeed, by changing this position of the slider, we attach some resistance in parallel to R2 and R3, making the total effective resistance more or less equal. But what is important that this so yes, it's important that we actually balance this bridge before start measurement, and then when we balance it, then we could continue this measurement. Well, This is a bridges. These bridges, what we consider actually are DC bridges, and they are suitable for the measurement of the resistance only. If we are going to measure other type of passive elements, some capacities or inductivities, so we have to use another type of bridge. So we need actually special bridges for such a measurement. Why? First of all, if we are going to work with a capacitor, we know that the DC current just doesn't flow through the capacitor. When we speak about the measurement of the capacities and inductive loads, we have to bear in mind the effective circuits of such devices. When we speak about a capacitor, so we never have a absolutely ideal capacitor. The capacitor may have some kind of leakage resistance. So for to understand the concept of leakage resistance is quite easy. That it's actually some current that flows through the dielectric, through the dielectric of the capacitor, or it may flow over between the electrodes of the capacitor because of the moisture level and so on. From this point of view, this scheme, it looks like more simple. So we actually may easily interpret what does the capacity means. It's a real capacitance of the capacitor, and what does it R mean? This resistance. It's actually leakage resistance. It's maybe not a dielectric in a capacitor is in response for this. It's responsible for such a behavior. It may be the moisture film, which always at the room temperature is around any object, yeah, and some current flow through this moisture. Never mind. So this is the idea of this parallel connection of the capacitor and resistance. This equivalent scheme is used. It's not so easy to understand what the idea here, what to interpret what the resistance is, what this resistance is. Yeah? But as the practice demonstrates and theory demonstrates that we actually may use both of them, no matter. Of course, they will have, at the same capacity C, they have a little bit different parameter of the, quite different parameter of the resistance R and resistance R here. So they will be different for two different model. Yep. So, well, the same is in force with chokes, with inductive elements, and here quite straightforward to add the resistance of the wire itself in series with the inductivity. So using the equivalent circuits, we consider that the capacitors are ideal, so there is no any DC current through it, also it may be. For the inductivities, we write them as usually interpret them as the ideal, so they have no resistance at all. And then to take into account that in fact every real resistance has some resistivity. Every real inductivity has some resistance. We actually add this resistance here. Some parameter with a capacitor, so-called dielectric tangent, is very often used, and it is a ratio for such kind of circuit. The dielectric tangent is a ratio of 1 divided by omega RC, where RC is a multiplication of these coefficients, and omega is the corresponding frequency of the signal. For the inductivities, we just let's remember such a value as a inductivity, and actually the charge flow that may go through this inductive load. So the parameter of the inductivity is so-called quality factor. It's actually ratio between omega L, which is active resistance, reactive resistance of the inductivity, and the resistance of the inductivity. The higher this value is, the less is resistance, and the more inductive is behavior of the particular particular choke. Well, if we consider a measurement of the capacitor in the bridge, of the capacitor in the bridge, would we will be able to perform this measurement to balance the bridge? First of all, of course, we should understand that in such case, when we use a capacity, we wish to measure the voltage, the parameter of the capacity, we have to switch to the AC current. We have to switch to the AC current, and then the AC current could flow through the capacitor. But would we will be able to balance this bridge? What do you think? Is it possible to find such a combination of resistances R2, R3, and R4 to actually to get the voltage between points 1 and 2 equal to 0? No? Any ideas? Why? First of all, yes, you're right. Capacitor is a reactive element, and its impedance will be changed with the frequency. But when we take some certain particular frequency, let's consider the balance equation. So we have to provide the equality between these two products, Rx times R4 is equal to R2 times R3. So this is already known balance equation. So when we come to the AC circuit calculation, we know what to do. We replace our resistances with corresponding impedances. And now we have to replace the impedance of our unknown capacitor. Actually, we actually have to use the impedance of the unknown capacitor. And impedance of the capacitor is already in a complex number. So we will have, this is a leakage resistance of the capacitor, and here is actually a reactive resistance of the capacitor, which is depending, of course, on frequency. But if we open the parentheses, we will actually see that we have a complex. We actually have to consider now the equality of two complex numbers. What does it mean that two complex numbers are equal? It means that both real part are equal and imaginary part are equal. So for the real part, it's very fine. All is very nice. Yes. So we just have to balance the RC, R4 product with R2, R3 product. So this is okay. So we may find such a combination, for instance, by changing R2 or R4. We may finally get a equilibrium here, or let's say balance the real parts. But what with the imaginary part? So we have here the imaginary part too, but there is no any imaginary part on the right side. So it means that whatever we do, we never could balance this bridge, because we may balance it as good as possible by balancing the real part, but we couldn't balance it because we have only one reactive element. So what should we do to be able to balance the bridge? How could we change the circuit? So what is the problem? The problem is that in this balance equation, we have no imaginary parts here, no any imaginary component here, and we have here both real and imaginary components. So what should we do to be able to balance? We need to add capacitors that adds some imaginarity. If I could say it like this, some imaginary component here in the right side of the equation. For instance, I may replace R2 with some capacitor. So I need to add it here. So in this case, my equation immediately changed. So I got here not only, I will still have the R2, C2. I will still have R2 in this real part balance, but I have this impedance of the capacitor C2 in the imaginary part. So, and now I may balance a bridge. And this is one of the differences between DC and AC bridge. So in DC bridge, we usually have to adjust only one parameter, one of the resistances. In the AC bridge, we actually have to adjust two parameters. So the balance of the AC bridge is a little bit complicated. So we actually have to balance two parameters to counterweight our measured capacity. So we need to change. For instance, we may balance this capacitor C2 and the resistor R2 to balance both of them. So then we could get this to balancing. Practically, it may look like this, as I said. So we have a balancing resistor R2, which is actually a magazine of the or resistor box. This is a resistor box that we may change. And we have, for instance, we may have a calibrated calibrated capacitor, regulating capacitor. So such a capacitor, so the capacitor, which capacity we could change, which capacitance we could change, looks like this. So this is one of the very old examples. Ear capacitors, so the capacitors provided with by use of these metallic plates, but the dielectric is here. Sometimes these capacitors, if they are for the high voltages, or we need a little bit higher capacity, may be immersed in oil, having a big dielectric constant, and the capacity will be increased. Generally, it's fine. So how actually the balancing will take place? So we adjust one of these regulating elements, looking at this meter, and we need a meter which shows us at least the amplitude of the oscillations, because the voltage between 1 and 2 will be alternating. Then we have to see on this amplitude of this oscillation. So we regulate, for instance, R1 until we get a minimum of this amplitude. Then we start to regulate C2 until we get next minimum. Then we still should reattach a little bit one more this R2 because change in the capacitor will disbalance bridge a little bit. And so in this measurement we usually go in such an iteration. So we adjust one parameter to get a minimum voltage, then we adjust the second parameter, then one go back to first parameter, and then we go in this way until we will get the zero in this voltage. Frankly speaking, so this example is quite poor, and there is two reasons why it is poor. The first of all, it requires alternating capacitor. No, generally, alternating capacitors are either more expensive or much more less accurate. We have seen the capacitor box too. Last classes we see this capacitor box. There was a capacitor box on the market too, but they usually have a less accuracy. If you're going to have an accurate measurement, it's much more easier to get an accurate resistor boxes. Second drawback of this circuit, as I said, we balance this circuit in some kind of iterative process. Balance R2, then C2, then one more R2, then C2. So this bridge requires quite a number of such steps to balance the bridge, and so the convergence of this process is quite poor. So we have to use quite many steps. A good bridge, alternative bridge with alternative design, we may reach the balance approximately after 2 iterations, for example. So one times resistance and capacity, the one more resistor, and then actually already here we are. Some modification what could be made. One of the simplest modification is if we are in luck of such alternating capacitors, we may use 2 resistors to balance a bridge. So because no matter how we balance this part, so we see if we have some unknown capacity C, resistor R4, so we may actually, and the capacitor C2 is actually well known, we may balance this part by changing either R4 or I3, so it's kind of convenient. So it means that we may balance reactive part without changing reactive element. So you have here some capacitor that is already embedded for eternity in this bridge, and then they regulate resistors, which resistor boxes are much more accurate and cheap, I guess. But such an example, when we balance actually resistors R2 and R3, so we actually uh, could find the relationship between the capacitor resistance and capacitor capacity when they have only resistors when could regulate only R2 and R3. Yeah. And this modification doesn't require capacitor, but it's quite poor just because of poor iteration, poor convergency. To get a good convergency, some other type of bridge was used, and one of the bridges is so-called Wien bridge, which has a balance rule at a particular frequency omega, like that. So whatever frequency omega we use, so we have the same, it's this balance rule. And actually, this may be rewritten. So there is two actual rules: the first rule and the second one. So to get these rules, how to say, so to satisfy these rules, we may regulate just two resistors R4 and R2. If we change them, and from this we actually may get all other parameters of the Wien bridge. In fact, we actually balance the bridge and get the relationship between, finally, when the bridge is in a balance, when the voltage amplitude here is zero, or at least as close to zero as possible, then relationship between the capacities will be expressed like this. Quite a similar, not absolutely similar, but something similar is in situation with in inductivity measurement. So with the inductivity, the situation is even poor. So if we have, actually, I have seen many times a resistor box. I sometimes have seen a capacitor box, but very seldom could see an inductivity box. So then the measurement of inductivity is preferable to have a measurement of inductivity when you don't need to have an alternating inductivity. And here the Maxwell bridge will help. And please note that we are going to measure inductivity, but Maxwell bridge doesn't contain any more the inductivities, and the only reactive element is this capacitor. So such type of a bridge for the measurement of inductivities is called the Maxwell bridge. Here is an example of modern bridges which are used to measure the parameter of the discrete electronic components with extremely high accuracy. They are very accurate. And nowadays, mainly such kind of all proposed bridges are manufactured. So nobody care now about bridge which measure only resistances or only some capacitance and so on. So we use the bridges that measure any parameter we wish, and for the estimation of the single electronic circuitries elements like capacitors, resistance, inductivity, shocks. So other parameters may be measured too. So it's measure the for the inductivities. It's measure not just an inductivity, but it's measure the quality factor. It's measure phase angles, and so on. So here is shortly about bridges for AC. And so should we take some break now, or we could continue? Okay, probably we may. Let's take some 5 minutes break now, even 7 minute break, up to 1:30. Yep. So let's continue. The second part, what we're actually going to discuss in this topic, it's a measurement of electromotive force on of a voltage. When we speak about the measurement of the voltage from the source, which has a quite high equivalent resistance, we should be careful because our meter with a limited input resistance may distort the measurement. So here is a quite, we already discussed this, I guess, when we discussed the input impedance, the effect of the voltmeter resistance to the measurement of the electromotive force of some small power element. If we have a voltmeter with an infinite resistance, so our measurement will be accurate. But when the resistance of voltmeter it's finite, so we actually have to take into account that the current that caused by the electromotive force here will flow both through the internal resistance of the source and via the resistance of the meter itself. And then we actually measure not a total electromotive force or not a total applied voltage, but only this part which falls over the resistance RV. We could easily understand what happens if we move the situation up to the absolutely stupid case when we just drop the resistance of the meter up to 0, the measured voltage will be just 0 because the voltage across the 0 resistor always is 0. What should we do to prevent the meter from affecting the loading our electromotive force source? We may use so-called compensation circuit. So here is the idea of compensation circuit, the simplest idea of the compensation circuit. So we have some source of the voltage, stabilized voltage source, and we have a potentiometer. Sometimes it was a very, very long, many time ago, let's say, for the very first measurement, compensation measurements, these potentiometers was made in the form of so-called real cord. So it's just a wire, a long wire with a high resistance. We know the length of this wire, and the sliding contact, this moves over the wire, actually divides this long wire into two parts with different resistances. But the most important is that the ratio between resistances was actually equal to the ratio between lengths of the wire before sliding contact and after sliding contact. So that allows to make the measurement with the compensation circuits without even measurement of the resistance of the wire. Nowadays, of course, potentiometer are used, calibrated potentiometer are used. So the idea of the measurement of the compensation circuit is the following. So we have to have this voltage UB higher than the measured electromotive force or voltage E, and we connect the measured voltage or electromotive force source in such a circuit to the sliding contact of the middle contact of the potentiometer, and we include the ammeter into this circuit. So actually what we are doing, we are adjusting the position of the potentiometer until we got a zero current in this circuit. What does it mean, zero current? It means that when we will have a zero current in this circuit, very easy. We will have this current zero when, so we will have this current equal to 0, and that moment, or in this situation, when the voltage here is absolutely equal voltage here. I mean, voltage over on the output of the potentiometer will be absolutely equal to this electromotive force. So in fact, this resistor, this potentiometer form a voltage divider. It forms a voltage divider, and the output of this voltage divider, when it equal to the electromotive force of this element or the voltage of the source, so when they will have the voltage here is equal to voltage here, and then no current flow through this meter. Such a compensation circuit, the main advantage of this compensation circuit, it doesn't load the source. So we may measure the voltage without letting the current flow in this small circuit. In such a simple circuit, what we actually need, we need in fact a calibrated potentiometer. So we have to know exactly what is the ratio in any position of the slider of the potentiometer. We have to know exactly the ratio between this resistance and this resistance. So, and we need a stabilized source. So I mean we have to know what is the voltage provided here. Knowing this, yeah, we may estimate the measurement. We may measure the voltage by making a compensation and then calculating the voltage in this point, knowing the stabilized voltage and knowing the ratio between upper voltage and upper resistance and lower resistance of this potentiometer. Such a circuit, it may be easily automated as well. So here is example of automated circuit. So we still use a controller motor. And to measure the current in this circuit, we apply here additional resistor, like shunt resistor. So we know how to convert now current into voltage, and the voltage that will be measured from this resistance, it should be measured with an instrumental amplifier as well, because it doesn't. No one point here is connected to zero, so it's more easily to use the instrumental amplifier. So instrumental amplifier measures the voltage across the resistor R0, and if this voltage is not zero, provide a control signal for the motor. The motor rotate shaft to change the potentiometer position either up or down. So of course we need to adjust the right movement, a correct direction of movement, when the change in the potentiometer position should cause the decrease in the voltage drop over R0, so decrease the current. So it goes should the direction of movement of the motor should be in the direction of balancing of the potentiometer. So the electromotive force here for the potentiometers actually, for the potentiometers, they are mainly these different sources of voltages, which are these sources which are not provide a high current. So this source may be a transducer such as thermocouples. So usually for the thermocouples, nowadays it's not so very actual because we have quite a high input impedance potentiometer amplifier to work with thermocouples, but it may be thermocouples, it may be some kind of chemical devices. So it means the devices that provide voltage, but couldn't provide a high current. And then to measure this current with as low distortions as possible, we may use these potentiometers. Another limitation of the potentiometers, as they use mechanical balancing, so the real motor, which has to provide real movement of the real shaft of the potentiometer, they are quite inertial. So we couldn't use them to measure. Very fast processes. So this is a limitation. And finally, another circuit, the last circuit we can consider today, is a circuit for the high accuracy compensation. So for this scheme, for this circuit, we have to have a stabilized and well-known UB, the voltage applied to the rear hub. Not always for the high class measurement, it may not be enough. So we need more accurate measurements that allow us to compare the voltage of or electromotive force of our measured source with some very well defined electromotive force or voltage. And for this, we may use such a compensation, high accuracy compensation circuit, that is based on the use of so-called normal elements. So these are half of so-called normal cells. So these are these normal cells. The normal cells are made of the mixing for instance, mixing two metals or using two metals in a certain very well-known chemical buffer, like sodium chlorine or potassium chloride or something like this, or so actually two metal immersed in a single electrolyte. They provide a very well known, very well stabilized voltage, and these voltages are well known from the 19th century when the extensive electrochemical research was made. So, for instance, for these normal elements, you may see that such elements provide an accuracy of its voltage up to fourth digit up to the fourth digit here. Yeah? So the accuracy of these elements is one of the highest, and it depends actually of the purity of chemical compound those elements are made of. So we may use very often we use mercury as one of the elements. You use mercury. You may use copper and zinc. We may use other elements, but every normal elements, they provide very accurate voltage, but they are absolutely unsusceptible for current. So they couldn't keep high current. So if we try to load them, first of all, this voltage will drops, and the second, the element actually depletes very fast. Depletes very fast. So we need to measure them with as low current as possible. Well, so how to do this compensation? So in this case, we are not sure. We may not be pretty sure about the voltage here. It's not necessary to provide very stable voltage. We still have to know well the relative position of the slider in a potentiometer. We have to know what part it occupies. We have to have a very accurate potentiometer, but we may actually neglect some accuracy in the power supply. So how the process actually happens of this high accuracy compensation? So first of all, so the connection is very similar. So here we still have this connection for the measurement for the compensation of the measured electromotive force, but here we have additional circuit for the compensation of this normal cell, and we need 2 amps. One important feature of these amps, they are not necessary to show us voltage or a current. They should indicate 0, whether we have current or we have no current. Well, so first of all, so we use it's a different way how could we do this, but usually we roughly balance here with any position of resistance R0. This R0 work as a just alternating resistor and allow us to change the total resistance in a circuit containing resistors R0, R2, and RK. So we may just change the current here. And we actually do. We change the current here. And by changing the current, we change actually the voltage drop over the resistor R2. Changing this voltage drop of the resistor R2, we regulate the current until we got current I2 equal to 0. When we got A2 equal to 0, it means that the current that flow here is actually times R2 is equal to A0. So we need to have a resistance R2 very well known as well. So we balance until we get the current I2 equal to 0, and in this moment I0, the current circulating here, times R2 will be equal to A0. Knowing R2, we may calculate current I0. The next, we balance this circuit until we got the current I1 equal to 0. When we has no, before this circuit was balanced, the current that flows through the resistor R2 was actually split into 2 currents, the current A1 and this residual current that continue to flow through RK. So when we stop the current I1, this total current may little bit change. So sometimes after the second regulation of the zeroing current in this circuit, in this part of the circuit, we have to readjust the current R0. Sometimes we do 1-2 iterations, but finally by adjusting R0 and the position of this potentiometer, we have to got both current I2 and I1 equal to 0. And when, so actually this circuit is in balance. And when they are in balance, in this case, when they are in balance, we actually have this equation allow us to estimate current I0 that flows through our car, and the measurement electromotive force AX will be equal to the voltage UK, which is the resistance RK times this current I0. So this is actually the way of how we provide this high accuracy compensation. Okay, so please, any question about bridge measurement? So no any questions so far. Well, okay, I think that we'll end with this for today. So we skip the second lecture today, and we continue next week, yeah, and we will discuss the digital measurement circuits, and even probably we'll start some small practice in Arduino control. Well, okay, so thank you. Yep. Yes, we do. Yes, we do. Probably you had some. Yes, I now understand. We actually planned it a little. First of all, we planned it a little bit denser this lecture, and that's why I skipped some of them without any problem, because we was waiting. We actually was in hope that the end of the semester will be practical placement. At the moment, we have not, still have not isn't able to provide a practical placement for you. I mean, the practical, but laboratory classes. And probably we will go with the lectures until the end of the semester, trying to compensate the laboratory classes at the next semester. At the moment, yeah, we will have these classes at Tuesday. And if we will have some change related to the laboratories, I just inform you. So we will adjust the schedule. Yes. Okay. That was a question why we do we have classes or not? Yes, we do. We still do, and we will have some practical training, what we may do online about the programming, controller programming, and then we will see what actually happens. Yeah. But probably we will have mostly the lectures. Unfortunately, because it should be good to have some practical classes. But then it means that we maybe concentrate on these practical classes, more concentrate on the practical classes next semester. Okay, so yeah. So bye bye.